Uh, Thank you, Pablo. So, thank you for inviting me for give a talk on the Einstein Toolkit workshop. And I'm going to talk about our numerical relativity framework, Dendro-GR. And I want to emphasize that this is this is not on the research done in collaboration with my colleagues William Black, Andrew Carroll, Eric Hirschman, and David Nielsen, Hari Sundar, and David Van Komen. So in terms, if you think about numerical relativity and with increasing accuracy of these gravitational wave detectors, we need more faster, efficient, and accurate numerical relativity codes. And in terms of achieving this goal, I think we can make improvements for NR codes based on this in three areas. We can design more efficient computational methods or efficient numerical methods such as new discretization techniques, etc. And also we can have leverage the improvements in computing hardware. And also I want to emphasize that the computing hardware has improved over time, but they have become also complicated to use or complex to program if you are interested in getting more performance with these heterogeneous computing architectures. And also what should performance portability in numerical relativity codes looks like, and how to achieve those things are important in order to do science with these numerical relativity codes. So in my presentation, I will try to focus on all these three areas and how we focus in each area, how we try to improve our Dendro-GR framework to achieve more faster and accurate numerical relativity simulations. So if one of the main challenges in numerical relativity community is basically computing this large mass ratio binary mergers, and people have made previous attempts to do very high mass ratio binary mergers. But this is if you look at the binary black hole parameter space, this large mass ratio binary mergers, we have very little simulation data or even no samples in some regions of the parameter space. And this is because when we increase the mass ratio, we require the smaller black hole to keep increased refinement, and most numerical relativity codes use explicit time integrators. And because of the CFL conditions, our times when we refine the smaller black hole, we increase the spatial resolution, and also we increase the time resolution governed by the CFL factor. So basically, that's why this large mass ratio becomes very expensive to run. And so in order to reduce reducing simulation costs, I think in Dendro-GR, we address this by having more efficient localized adaptive refinement, and also having more scalable codes that can perform numerical relativity simulations faster, and also try to leverage the use of GPU accelerators. So very brief overview of the Dendro-GR framework. So Dendro-GR is based on the octree framework named Dendro, and it supports Dendro has all this library suite for supporting octree generation in distributed memory setting, and all this adaptive grid generation part is handled by the Dendro framework. And on top of that, we have added a symbolic code generation framework. I mean, if you are familiar with, if you have worked in the numerical relativity, I mean, Technically, you can write these code these equations by hand, but it's going to be a tedious task. So most people use some sort of a code generator to evaluate the right-hand side of these PDEs. And we have a simple code generation framework that is native to Dendro-GR. And also we do support GPU accelerated simulations. And currently it only supports for NVIDIA GPUs, and we are working on making it performance portable. And it is highly scalable. We have shown good scalability. What I mean by scalability here is if you increase the problem size or the degrees of freedoms in your domain, and if you can if you can put more compute resources, can we keep the time step constant? That's what I refer by the scalability here, and all our codes are openly available, and you can find this Dendro file library, which does all this octree generation stuff, and it has been used for other computational simulations as well. And you can download the tailored version of the Dendro-GR, which has basically do this numerical relativity simulations. So, brief overview of how we drive our adaptivity. So our adaptivity is driven by this wavelet expansion. So the basic idea is in the wavelet representation, a sparse representation of a function. So for a given function on the grid, it is captured by the features in the you can say it has a coarser resolution, and the information not captured by the coarser this coarsest level will we use the information in the next refinement level. So you can see this is hierarchically builds up. So for each level, if the information is not captured at that level, we use the information at the next final level. So this is what exactly what this wavelet coefficients represents. So basically, we try to reconstruct the solution at the final level from the previous coarser level, and we see how much of an error we make if we try to reconstruct the solution at the final level. And if this error is too large larger than the specified threshold, we decide to keep the final level or eliminate the final level. So this is basically the idea of the wavelet representation or the sparse representation of a given function. And this is in order to do this in 3 dimensions, we use octree as our primary data structure. And as you can see, the hierarchical nature of the wavelets are also represented. I mean, naturally comes in the octree data structure. So if you are not familiar with octree data structure, octrees are naturally arise if you have a 3D domain, and if you each split each dimension hierarchically, each non-leaf node will get 8 children. I have shown a 2D example. In 2D, you get a chord tree where each non-leaf node has 4 children. So basically, you have a 2D domain. You basically split each dimension hierarchically, and based on how you refine, you can decide to refine each region of the domain depending on your refinement criteria. In this case, we use this the wavelet stuff, and we use our Dendro framework, and it has efficient routines to compute this, evaluate these fast wavelet evaluations to drive our refinement. So how do we drive our refinement in our simulations? Instead of defining predetermined levels in our region, in the wavelet AMR, we specify a wavelet tolerance, which basically says how much how much error that we can tolerate when we are reconstructing from the causal level. So the idea is for a given wavelet tolerance function, which can be a function in both space and time, and we will try to keep the finer features if our wavelet coefficients are larger than this specified tolerance. And the main motivation for this is this instead of doing predefined adaptivity, we think that the wavelets can capture the evolving solution more localized adaptivity with more systematic error control rather than we guessing we need this much resolution in this region. And these are some of the grid structures generated for mass ratios 2, 8, and I've zoomed in the grid structure of this mass ratio 8 run on the smaller black hole. And here we can see how this the wavelets automatically capture this propagating wave front. And here are some example grid structures for Q equals 4 and Q equals equal mass ratio binary merger. And you can see, at least we can see that there are some the trailing behavior in the Q equals 4. So this is entirely handled by the wavelets. We only specify the wavelet tolerance, and it automatically determines where to refine. And it's we don't basically say specify a refinement level. So everything looks good for Q equals 1 and Q equals 4 cases, but we found that this wavelet refinement was not performing well for when we go to even large mass ratio simulations. So this is an example of Q equals 8 binary merger, and you can see because of we found that in our simulations with increasing mass ratios, this initial lapse wave is you can see it's more pronounced. And for the wavelets, it's hard to define whether this is it will identify this is something that variability in our solution, and it starts refining. So that's what you can see here. So we start the Q equals 8 simulation with the initial lapse wave. You can see the wavelets refining on that, and this can become more expensive because to carry this lapse wave, it requires a lot of resolution. This spherically expanding wavefront.
Milinda, this is Pablo. I have a quick question. So
Yes.
there are many variables in the simulation. So which ones do you use to determine where to refine?
Currently, we use all of them.
Okay.
Yeah. We have tried to use subset of those, but we found that in order to get more accurate simulation, we need to refine based on all of them. Yeah, all the 24 variables in the BSSN formulation. Yeah.
Thank you.
Yeah. So how we tackle this problem? So basically, as I mentioned, we can specify our wavelet tolerance. So the previous simulation, this wavelet tolerance is specified constant value in globally. So that's why this problem happens. So in order to tackle this problem, we decided to try with the wavelet functions that depends on the space and time. So the idea is we want to have the lower the wavelet tolerance, That means you are more likely to trigger refinement. And the coarser or higher wavelet tolerance is less likely to trigger refinement. The idea in the tackling this problem is to define a space-time dependent wavelet tolerance function. So we wait till this initial gauge wave propagates out, and then slowly decrease the wavelet tolerance in the regions that we are interested in. So this is the main idea of this space-time dependent wavelet tolerance. So basically, we wait till the initial gauge wave has passed to refine, to hand it over to the wavelets. So these are some of the wavelet tolerance for different wavelet tolerance functions. I mean, this is something that user specified, and this is on different snapshots of how this wavelet tolerance function looks like at time equals 0, where we have very high, very low tolerance, very close to the black holes, but at time 20, we assume that the gauge wave has passed, and we try to increase the tolerance in the more reduce the wavelet tolerance in more regions in the grid. And so these are the wavelet-based runs that we have done in previously, and these are different refinement functions that we used, and basically the epsilon min is the minimum wavelet tolerance used, and epsilon max is the 10 to the minus 3. That is like further away after further away from the extraction radius that we are extracting gravitational waves. And these are the SUs that we have used for each of these runs. And you can see this Q equals 16. We have used a lot of compute resources, and we found that this our old wavelet refinement criteria needs some tweaking to be done. So maybe the wavelet tolerance function that works for Q equals 4 might not work well for Q equals 16. And this is for the Q equals 16 run, we had this gauge wave, and it was we were refining this gauge wave until it reached the extraction radius, and it slowly dissipate because we increase the wavelet coefficients. That's why the Q equals 16 run was that expensive in this case. So in order to improve this refinement strategy, and we also found that if you use only the wavelets, and if you compute the higher order spherical modes of the extracted gravitational waves, they get decayed pretty fast, because wavelets because they have lower magnitude, and wavelets it's hard, depending on the wavelet tolerance, wavelets say to coarsen the region of the extraction radius, and because of that we can see these higher order extracted mode damp very quickly. And we were thinking, actually, William, who was working on that, came up with a efficient, more systematic way to improve the refinement. So the idea is use the orbital frequency to estimate the for each LM mode to approximate the wavelength of the gravitational wave, So basically, we can approximate the orbital frequency during the simulation, and based on that, we can approximate what is the wavelength for different LM extracted modes. And based on that, we can determine based on the Nyquist criteria, we can determine what is the minimum resolution required to capture these propagating waves. So this is what what is done in this orbit refinement scheme, and you can find more details in our most recent paper. And if you use this orbit refinement, it basically, and we had done some tweaking for this our wavelet AMR algorithm. So basically, we wait till the initial lapse wave is passed, and then start refining on the gravitational waves or during the in spiral. And also this orbit, we use this orbit algorithm to enforce a minimum resolution in different regions of our in our grid. So based on this wavelength and the Nyquist criteria. So even though sometimes wavelet might say we can coarsen in this region, if it violates this orbit refinement criteria, we are not coarsening the grid. So this has improved the extracted higher order gravitational wave modes. So you can see without this orbit turned off, you can see these high order L modes damps quickly, and with this extra refinement enforced based on the extracted wavelength and the Nyquist criteria, we can see that we can capture them more accurately. And this is a more systematic way to, instead of tweaking the wavelet tolerance function, I think this is more systematic way to do this. Depending on what L modes you want to extract, we can determine exactly what refinement levels we needed. So all these improvements for our refinement criteria, and it takes time to figure this out because the NR simulations are costly. And tweaking this refinement criteria took us some time. But with this improvement refinement criteria compared to this compared to these runs, so these runs were done in 2022, and that is referred to as this 22 version of the refinement criteria. And we can do with the tweaking of the wavelets, we can run with this orbit refinement enforced or orbit refinement without this orbit refinement, and it has reduced this for some cases with the orbit refinement, because it enforced this additional refinement on the extraction regions, it little bit increased the number of degrees of freedoms on our grid. But overall, when we are going to large mass ratios, it has significant, especially for the Q = 16, it took roughly 57 days to complete for the complete simulation, but it has reduced, this refinement criteria has reduced it for 25 days. And you can see it also has reduced this Q = 4 run from 12 days to roughly 4 days with this improved refinement. And we are targeting for Q = 32 and Q = 64 binary mergers as well currently. So just for verification, we have done like convergence with respect to the wavelet tolerance. This is here we have done like a self-convergence study on the error in the extracted wave with decreasing wavelet tolerance. You can see when we decrease tolerance, we enforce more refinement And you can see the errors in the extracted waveform reduce. And also we have done some cross-code verification with the LASIF code with the low and medium resolution run, and you can see with increase in refinement, we converge to the solution that is in the computed by the LASIF code. And I will now go over some of the performance improvements that we have made in our Dendro framework. And I think one of the key features that we add was the GPU acceleration of our BSSN solver. And the main idea is we perform our grid generation on the CPU or on the host, when we want to do this time integration of the BSSN equations on the GPU. So basically, these are the operations that are color coded are the ones that are offloaded to the GPUs. And I mean, if you this octant to patch representation is basically where we go from this octree representation to this buffered with each element get a buffered region for evaluating the derivatives using finite difference schemes. And the right hand side is basically the BSSN right hand side evaluation. And then once it is done, comes back to this patched more patch to octant, which is more compact representation. And basically we do whatever time integration scheme that is specified. And so these are the routines that is handed over to the GPU. And when we are doing that, we found we need to do some tweaking for the symbolic code generation. I think for the GPUs, the one that we mainly learned was evaluating the BSSN right hand side on the GPUs cause a lot of register spilling, and that can reduce the overall performance of the right hand side evaluation. And in order to mitigate that, in our SymPy-GR framework, we try to build the computational graph and use some graph traversal algorithm to reduce this register spilling issue. And you can see as a performance comparison, if you run just the SymPy-GR with the baseline code, you can see the amount of spill loads and spill loads. So basically, this is compiler reported register spillings when evaluating the BSSN right hand side. And these are some of the improvements that we make, and we can reduce the register spilling. And this is reflected in the average speedups that we can achieve. And we did our performance comparisons, and for the right hand side evaluations, we can, for the time integration with GPU acceleration, I mean, these are memory bound operations, and also we have this heavy register spilling issue when evaluating the BSSN right hand side. And we were able to get like 2 to 2.5 overall speed up compared to the using CPU time integration. And in these plots, I've shown for different number of octants, what's the time per octant, the right-hand side evaluation cost between using the CPU-based BSSN right-hand side evaluation and this using this GPU right-hand side. And here I have shown basically the overall time integration cost. I think this is for like 5 RK time steps between the CPU time integration and the GPU time integration. And also we have shown good scalability. I mean, this is important when we especially want to handle large mass ratio runs. So basically, when we increase the mass ratio, we are gonna increase the number of degrees of freedoms in our grid. and see if the scalability is important when to see if you can throw more compute resources at it and see if we can maintain constant time integration cost. And this is where we have done a scalability study on this Frontera Texas scale run, where we have scaled, I think, almost to the half of the machine, and our full machine job was for some reason did not run, and I think scaling to 260 to 29 cores is more than enough for us at the moment. So for in terms of ongoing work, so we are exploring the compact finite differences. So if you are not familiar with compact finite differences, so regular finite differences, we approximate the derivative at a given point by using the neighboring information or the function evaluation, only the function evaluation, and depending on the stencil order, this width of the stencil increases. In the compact finite differences, we are trying to reduce this stencil width. So why this is important? This can reduce the buffer region reduce the cost of the buffer region computation, and also it can reduce the communication, the amount of information that needs to be exchanged between the partitions. So how does these compact differences reduce the stencil width? It's basically by involving the function derivative evaluation as well. So it will become like a implicit derivative evaluation, and this require a linear system solve. So we basically reduce the stencil width by evaluating the function derivatives as well. But this linear system solve that can be done, we can pre-compute this inverse of these operators and reuse again and again. So this can be done with the prefactored cost, and it requires application of smaller dense matrices with the reduced bandwidth, reduce width of the stencil. So these are some of the simulations that we try exploring using these compact differences. These are still at early stages. We are trying to do these head-on collisions, and you can see this is for the head-on collision using the BSSN formulation, use different stencil operators that we use, and the overall momentum constraints, the violation that we have. You can see that compared to so you can take the compact T4, which has a lower stencil width compared to the explicit 6 scheme. So basically you can reduce the stencil size and achieve the same accuracy as a explicit 6th order finite difference scheme. So these are some of the preliminary results, and we are still exploring this idea to reduce our stencil width, which can lead to more efficient simulations. And also we have implemented a spectral apparent event horizon solver, and the basic idea is you parameterize the horizon surface, use these spherical harmonic functions, and use these fast flow methods to converge for the apparent horizons. And we have verified it with the Edge Finder Direct, and we are in terms of ongoing work, it requires some performance improvements, and also need to add additional quantities of interest computations, such as computing the spins and etc. And so those are some of things that we are still working on. I think that's all I have for my presentation in terms of ongoing work, and I would that's all I have and conclude my presentation. Thank you.
Thank you very much, Milinda. Any questions for him from the audience here? Yes, Peter.
So have you, regarding your problem with your initial labs profile pulse that moves out, have you checked whether Scikit-Gen's slow start labs method works for these mass ratios?
Yes, I think for that's also something that I did not mention, but for this new large mass ratios, we are using this slow start labs, and it has improved this this initial gauge wave, and that's another improvement that we did for this large mass ratio runs. Yeah.
Any other questions? I have two questions. One of them is in the wave zone that you have in this problem that you found that you had to change the way you're doing this tolerance of this epsilon. Once that you fix it, how many levels of refinement you have there? I mean, in the wave zone.
I think in the you mean the maximum refinement level or the different refinement levels you have in the wave zone?
Yeah, and the way I mean the way I'm thinking is that as the wave propagates, I mean you have to refine how many daughters, so to speak, in the octree you have there. You have to use.
Oh, okay. So I think the waveform extraction region we have like the refinement level close to 6 or 7. So basically 7 levels of refinement where the maximum refinement in the grid was like 15.
Okay, all right. And my second question is about the time stepping. Do you have a local time stepping or is it uniform across the mesh?
So all these simulations that we did is using this uniform time stepping. And we do have local time stepping, but we have not extensively used it for the BSS runs. And I mean, uniform local time stepping, if you use your local time stepping, I think you can reduce this cost roughly by half, at least for our grids, because the most of the refinement, I mean, how the 2x speedup is great. So instead of this using 25 days, we could do it in 12 days. But it's implemented, but we have not explored the BSSN with that yet. Yeah.
Okay. When you use a non-uniform time stepping, do you have to reconstruct your octree at in every sub-step?
It's not a reconstruction, but the time we need to do a time interpolation between the different refinement regions.
Okay.
Yes.
I think Roland has. Thank you very much. I think Roland has a question. Is that right, Roland?
Sure. Yes. So thanks for the talk. This was very interesting. I see that you're making progress on this thing, and it's been alive. Do you have anything special that you do at the outer bound if you want to do longer simulations, or right now you just make your grid big enough and you call it a day?
I think right now we are making our boundaries farther away. If you want, then we don't have any special thing going on at the outer bounds here. So basically make it the domain bigger. That's the approach that we are using. Yeah.
Okay, thanks.
Are there any other questions? Any other questions for Milinda? All right. Thank you very much, Milinda. And
okay. Thanks for having me. Yeah.
all right. So I guess the question is, do we take a break and come back for a discussion, or you want to call it quits?
I think Roland said he will still be here for the discussion. Oh. So shall we just resume after 10:30?
10:30, that is almost 40 minutes from now.
Yeah, it is a long break.
Okay, let's just vote. I mean, let's for a change, let's be democratic. Now that things have changed. Or, you know, I can just unilaterally decide that we stop here, and then, what do you want? I don't hear any, Roland, he's gone.
No, I'm not going. You're not going to get rid of me that easily.
Okay, so since you're still the boss,
Me? No. Not
okay,
even that. Yeah.
Oh, actually, let me stop.
you're